Okay, last class period, we just started with the states of matter, learning about solids, liquids, gases, and then also some of the more esoteric things like a plasma, a colloidal suspension, and amorphous solid, liquid crystals. And I talked about these things. Fundamental differences, we talked about what comprises them. But the things you learn, like, in high school chemistry, you learn that solids have a fixed volume and a fixed shape. The truth is, a solid can be compressed, just not very much. So we consider it a fixed volume. And of course, solids can be deformed. You put stress and they do deform, but they don't deform much. So they're fairly valid approximations. A fluid, we say, okay, using the same terminology, what do you learn like in high school chemistry about a fluid? It has a what volume? Okay, you learned that fluids have a fixed volume, and what about their shape? Now, I made a mistake there, and I feel really bad. I said fluids. I should have said liquids. There's a big difference between the two. That's the point I'm trying to make here, and I messed it up. So a liquid has a fixed volume but a varying shape. The liquid will fill whatever shape it's put in. And once again, the fixed volume is an approximation. You can compress a fluid. It just has a very small amount of compression for a very large amount of pressure. And then for a gas, what rules do you learn about the volume and the shape for a gas? Not fixed for both. It will fill whatever you put it in, and it will take on whatever shape you put it in. So this room, it has air in here that's a gas, and the gas just completely fills the room. Now, on a molecular level, that means that we have molecules moving completely throughout the room, hitting the walls all the time. If it was only one gas molecule, we'd still say that one gas molecule is a gas filling the room, because it's going to go bouncing off all of the walls. So it's filling the entire volume. It's just at any moment it has, its location. So what we're talking about is the region that's having the interactions. So that's what you usually think of when you see these pictures, those things about fixed shape or not fixed shape, fixed volume or not fixed volume. I will not stop. I will not stop here, but move on to this question. Fluids are a special thing. Remember, I said that was my point. Fluids are materials that flow. They do not have a fixed shape. So of the things we listed, we said solids have a fixed shape and a fixed volume. Liquids have a fixed volume but not a fixed shape. And gases had neither fixed volume nor fixed shape. So with those definitions, now I put more things than just those basic states. A colloid, the suspension of a fluid in a fluid. Once again, using a term I'm trying to get of a liquid in a liquid. Is that something that will flow? Does it have a non-fixed shape? Yeah, it's a non-fixed shape, so a colloid will flow, so it's a fluid. What about a gas? Does that have a fixed shape? No. Hence, is it a fluid? Yes. Glass. Okay, I like Ryan's answer. He's bucking the everybody's heard that glass flows thing, right? Have you guys heard that? Ryan wasn't bucking it, he hadn't heard it. Okay. Does glass flow? Sure. Does ice flow? Sure. Does steel flow? Sure. In the solid phase, not in the melted phase. They still flow. Very, 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 very slowly. And so when people say, oh, glass is a liquid because, they say it's a liquid because it flows. No. It flows way too slow for us to consider it something that flows, a fluid. In fact, a physicist got so frustrated with people saying, oh, but glass is a fluid. he sat down and he analyzed things. You know, like people say, you look at an old pane of glass and you can see that it has ripples because it's slowed over time. And he said, well, okay, they put those in with lead. Is lead a solid or a liquid? Solid. But lead flows much more readily than glass does. And so all of the lead would have flowed out of the window, making the glass pane fall out, before you would have had any noticeable flowing in the glass itself. What he determined was, 100 years ago, they really couldn't make good flat glass. And what you're seeing is just the quality of glass making back then, not any flowing. Okay, so that's, I want to make sure I had glass in here. Remember, glass is an amorphous solid. And so solid doesn't flow. Liquid, does that flow?
Yes.
Yes. How about liquid crystals? Yes, because they're still liquids. What about plasma? Yes. What about solid?
No.
Okay, so there we've got it. Most of these things are fluids. That's what we're studying here when we talk about flowing things. Anything that flows is a fluid. Now, some important definitions. Density, I think we've talked about density a fair amount already, but now we have to be very careful. Density has this symbol that we use to define it. That's the Greek letter R, rho. I think I told you, imagine my confusion in graduate school. One of my friends was Greek, and we're doing like area of a circle, and she says it's PR squared. I'm like, P? Oh, I forgot. You Americans call it pi. Pi is P in Greek, and rho is R in Greek. And it's defined as the mass divided by the volume. It makes a big difference. Now, you have the simple questions that people answer wrong because they don't think it through. What weighs more, a ton of feathers or a ton of bricks? They're the same because they're both a ton, which is the weight. Which takes up more volume, a ton of feathers or a ton of bricks? Depends on what? The feathers are going to take up more volume because they have a lower density. And so this is, the picture here, of course, is not talking about, or it does not have feathers, it has hay. And hay is less dense than the brick, so to get the same weight of brick versus hay, you have to have a lot more hay. Now, just to keep in touch with what we did in lab yesterday, let us suppose that you had the same volume for hay as you have for brick. What would happen to this little teeter-totter? How could you make it so it's still balanced? Okay, for people who didn't see, Wes went, it's going to fall down with the bricks going down. How could you make it still balanced if you had equal volumes of brick versus hay?
The brick is much closer to the fulcrum.
Right. If you move the fulcrum much closer to the bricks, then you'll have the mechanical advantage, which will just be the ratio of the distance to the bricks and the distance to the hay. If you make the hay distance much longer than the brick distance, you can make them balanced again. Of course, it has to be done just right. Okay, so let me give you practical examples for density. When I was in graduate school, I was working with sapphire. Now, most people just think of sapphire as a gemstone and don't realize that sapphire is a very clear, hard crystal. And so you look at the sapphire, it looks like glass. You look at quartz, it also looks like glass. Quartz is just a crystalline form of glass, if you will. And so I have these samples, and I have to make sure that they're sapphire, not quartz, because we have identical samples of the two. And so the first thing I do is I measure the density. Because for a sample that's an inch in diameter, half-inch tall cylinder, because they have different densities, you're going to have different masses. So that was the first thing I did. Second thing I did was to measure the speed of sound through them. And the third thing I did was to actually use a Lowy camera to take a picture of their backscatter and make sure they have the right orientation. But the density was the first one because it's really easy, right? You put it on a balance, you know its dimensions, you can calculate its volume, boom. Now, force and pressure. This is my picture for force and pressure. I don't know why I have this picture. There's a lot of better ones probably. Force, you have learned quite nicely. Force is anything that pushes or pulls. Pressure is force applied to an area. Now, there is a stress and there is pressure. Stress is a tensor. It's not even a vector. Vectors have one direction. Tensors have two directions to them. And so if you talk about stress, you can have a compressive stress, such as I push on the table, I push down, the force on the table is down, and the normal to the surface is down. So if those are in the same direction, that's a compressive stress. If I glued my hand to the table and I pulled up, then the force is up, the direction of the table is down, they're opposite. That's a tensile stress. If I glued my hand to the table and I tried to go sideways, the force would be this direction, the normal is vertical. If they're perpendicular, that is a tensile stress. And then you have the different directions you can have for each one of those, which is, it's a 3x3 matrix is what we have for the stress tensor. So stress is force divided by area with directionality. We skipped over that section, so you didn't have any work on it. Pressure is basically the same idea. Pressure is also force over area. And so any reasonable person says, what's the difference? The difference is that pressure does not have a direction. Stress has, a 3x3 matrix for the directionalities. Pressure is the same in all directions. We tend to call it, if you want to be really specific, hydrostatic pressure. Hydro, because it's in a fluid. Static, because it's not a flowing fluid. If you have a flowing fluid, it kind of messes this up just a little bit. So pressure has no directionality to it. It's just force over area. So you kind of know if you travel like from here to Denver, and you have a tube of toothpaste, and you get to Denver and you open that tube of toothpaste, what's likely to happen? It comes squirting out. Why does it come squirting out? Air pressure difference. If you're in Denver, you're at a higher elevation, which means there's less air above you. The air pressure is the result of the weight of all the air above you pushing down on you or on whatever it's touching. And so you go to Denver, there's less air above you, hence less air pressure. And inside of your tube of toothpaste, when you closed it, it had the same pressure as the air pressure where you closed it. You open it, the pressure inside is higher than the air pressure. Remember, pressure is force over area. So the pressure inside is pushing on the toothpaste with a bigger force per area than the pressure outside. Well, if you have a bigger force pushing out than you have pushing in, it comes out. Every time we go to Colorado, something of my wife's toiletries spills everywhere. I probably shouldn't grin because, of course, it makes a mess and we're losing money, and you know I'm kind of tight that way. Okay, maybe you don't know. I am. But pressure is force over area. It's no directionality to it. Pressure is actually always going to create a force that's going into whatever surface it's touching. So right now, I put my hand out here, there's air pressure. The air pressure is about 15 pounds per square inch. That's not, it's like 14.9 or something like that. About 15 pounds per square inch, which means on my hand, if I take a 1-inch square section, the force of air is 15 pounds. So if I take my entire hand is what? About 9 by 5 or 9 by 4. Let's go 9 by 4. So it's about 36 inches. And if air pressure is 15 pounds per square inch, then the top of my hand has air pressure pushing down on it with 15 times 36. How many pounds is that? It's over 500 pounds. Just a little over 500. I said not to finish the calculation. It's over 500 pounds that's pushing down the top of my hand. And yet I'm able to hold it here because I'm full of muscle, right? Answer's all, yeah, that's it. Obviously, it's not because I'm full of muscle. How am I able to hold my hand here if I have 500 pounds pushing down the top? There's air pressure underneath that's pushing the bottom up as well. So I really don't have any difficulty holding my hand up here. Now I'm going to go straight to the concept of buoyancy. We'll study this more with Archimedes' principle. We'll do a lab on it. Buoyancy is the result of the air pressure being slightly higher in the bottom of my hand than it is in the top. Because there's a little more air above, if you take something out here, there's a little more air above here than there is here. How much? Very little. There's slightly more air pressure below, so my hand is actually being net pushed up by the air. That amount that's pushing up is really negligible. But when you get into a swimming pool, it's not negligible because the density of the water is about 800 times bigger than the density of the air, which says that if you go down an inch, the weight of water that you've gone under in that inch is much bigger, hence it's pushing up much more on the bottom than it is on the top. That's why we can float in water, some of us, but we can't float in air. What was that, right?
I said some of us.
Yeah, some of us. Only the skilled can float. That's what I'm going with. Of course, if people want to be truthful, floating has to do with density. Muscle and bone are dense. Fat is not dense. So people that have a higher proportion of fat are more likely to float. People with a lower proportion of fat, more likely to sink. But I like to say it's a skill nonetheless. Skill you develop with your dining habits. A classic problem for you. Let us say that we have a dainty 100-pound, LB for Libra, 100-pound person. And this person is wearing high-heeled shoes so that they have, and the person being an interesting person, they decided they're going to stand on one foot and then they lean back so all of their weight is on just the tip of their stiletto high heels. And so they have a little tip that has an area equal to, let's say, 1/10 of an inch squared. What pressure is that going to apply on that stiletto heel? Remember, what is pressure? Force over area. So that's going to be 100 libras over 0.10 inches squared. 100 divided by 0.1 is divided by 0.1, same as multiplying by 10. So it's 1,000 pounds per square inch. Go ahead.
Maybe I'm thinking about this wrong. Would a 0.10 inches squared, that would be just 1/10 of each square inch, not 0.1.
Right, it would be, if you want to say how big is it outside if you made it squared, is that what you're thinking? Or are you thinking something else?
Well, I was thinking 0.1 would be like 0.1 by 0.1, like the dimensions.
No, 0.1 by 0.1 would be 0.01 for its area.
Okay.
Yeah, so what you have to do is you take the square root of 0.1 to get the length of each side. And it's going to be what? Yeah, I don't know. So she would be making a pressure of 1,000 psi. Now remember, air pressure is about 15 psi. So that's about 7 times 15 would be, almost 7 times the air pressure. 70 times the air pressure. Very high. So a woman in stiletto heels can damage a floor by putting her weight on the heels. Now let's take a person that is a 200-pound person. And the area, now they're going to be standing on both feet. The area of their feet, take mine as just a classic example. It's what, about 14 inches long and about, let's say, 4 inches wide. So for each foot, it's 14 times 4, that's 56. But let's just round it off to 100 square inches for the 2 feet. What's the pressure applied by that shoe? Whoops. Yeah, that's going to be 2 pounds per square inch. Now, just, to go on the record, what would you rather have happen? Have somebody stand on you who weighs 200 pounds with both feet, or have somebody stand on you that weighs 100 pounds and put all the weight on the stiletto heel? Did you say the stiletto heel?
I said neither.
No, okay, neither. Okay, I suppose that's okay. I mean, there's, was it shiatsu massage or something like that, where the people are standing on your back or something like that. There is a massage technique where people do that. Of course, you don't want them to be too heavy. Let's just move on from there. Practical examples of pressure. We put air in our tires. We have pneumatic tires. Pneuma, God breathed into man and became a living soul, or there's pneuma. Pneuma is talking about air, actually, or your soul. And so we put air in our tires. We all know we have to inflate the tires, or else they'll be flat. Flat meaning you'll have the rim running on the ground, essentially. But how does putting air in there keep the rim from running on the ground? Yeah, it's got to have something to do with pressure, but it starts to get a little confusing. So first, let me introduce a few concepts. The first one is gauge pressure. Gauge pressure is the pressure minus a reference pressure. And the reference pressure we use in virtually all gauge pressures is atmospheric pressure. So a gauge pressure is the pressure absolute, that's the force per area, minus the pressure of the atmosphere. Now, I've used pounds per square inch so far. That is clearly not the scientific standard unit for pressure. The standard unit for pressure is going to be, what's the unit for force? Newtons, divided by the unit for area, which would be meters squared. So the scientific unit for pressure is newtons per meter squared, which we shorten to a Pascal. So a newton per meter squared is a Pascal PA. And 1 atmosphere is equal to 1.013 times 10, I think I got that number right, to the 5th pascals. So that's, if I do a gauge pressure, if I was doing it in the scientific things, a gauge pressure of 0 would mean your pressure is atmospheric pressure 1.013 times 10 to the 5th pascals. Now, we still are going to stick with, for the sake of practicality, using PSI, because we're all more familiar with how much pressure we put in a car tire in PSI. How much pressure do you put in a car tire in PSI? In pounds per square inch.
Around 30.
Okay, around 30 to 36. It depends on your car, your tire. So that is a gauge pressure. Got to change the color. Purple does not work with that picture. So we have pressure in is equal to, and let's go with 30 psi just because that's the number that he said. And that's a gauge pressure. So you have 30 psi, 30 pounds per square inch inside, more than there is outside. So if the outside is at, 14.7 pounds per square inch, then the inside is going to be at 47 pounds per square inch to make the difference 30. Of course, what happens if the temperature remains constant and you go from Lincoln to Denver? What happens to the air pressure when you go to Denver? it decreases. And thus, in fact, up in Hartselle, where our new house is, it's at 9,400 feet. The air pressure is like 70% of the air pressure down here. Very big difference. And so the air pressure outside is going to get smaller. What happens with pressure inside your tire? I said, assuming the pressure or the temperature stays the same. The pressure inside, the absolute pressure, stays constant. But the gauge pressure is going to go up because that's a bigger difference in pressure. So that's why if you go from here to Denver, your tires are going to appear overinflated because the air pressure outside dropped and the air pressure inside stayed the same. And of course, the reverse would be true if you go from Denver to here. Your tires are going to now appear underinflated because the air pressure outside got bigger. Okay, now staying with this. What keeps, one of your homework problems has to do exactly with this. What keeps that tire up? Well, we know that we need a net upward force. Let's say each tire is supporting 500 pounds, just to make life easy. So if each tire is supporting 500 pounds, that means if I look at the piece of tire that's in contact with the ground, I have force up from underneath and a force down, or force up, from underneath and force down from on top. The force down is going to be the pressure inside times the contact area. And the force up is going to have two pieces. It's going to have the pressure outside times the contact area plus the normal force. So we have those two. And I need the sum of those to be the upward force that balances the weight that the tire is supporting. I didn't draw the additional force there for the weight the tire is supporting. But what I need is the difference in those two forces is the weight supported. Well, if I use absolute pressure, then I'm going to have the pressure inside is the gauge pressure plus absolute pressure, plus atmospheric pressure. And then on the outside, I have atmospheric pressure. When I do my work, I would have, and I wish I had more space here. Yeah, I can't zoom or anything. Actually, no, those actually do equal 0. I did draw it all right. I didn't skip a force. So if you look at this, pressure atmosphere A and pressure atmosphere A are in both the up and the down. And so the force up minus force down is going to have pressure atmosphere A plus force normal minus pressure atmosphere A minus pressure gauge A. Nice. So I got to change colors. It's getting ridiculous. So these two pressure atmosphere A's subtract out. And what I end up with is the force normal is equal to the pressure gauge times the area of contact. So the amount of force that the tire is supporting, the force normal, is equal to the gauge pressure times the area. So if my tire has to support 500 pounds and it has 30 PSI, 30 pounds per square inch for the gauge pressure, then I would have area is equal to the force normal over the pressure gauge equals 500 pounds over 30 pounds per square inch. Wow, I went 2. So 500 divided by 30, 50 divided by 3 is 16.6 repeating. So you need 16.6, to say 16.7 square inches of contact area for that tire to support it. If you lowered the air pressure inside, what would that do to the contact area necessary? It would increase it. Hence, the tire gets closer to the ground because it has to flatten out more. And so you can actually determine how much weight each tire is supporting if you can determine the contact area for the tire, which of course you virtually cannot do. But your homework problem has a bicycle tire, and that's what you're doing. So you're basically repeating this calculation for the bicycle tire. I already talked about buoyancy, so I can skip by that one. Now getting to a little more in-depth calculation, how pressure varies with depth. I've already said that the air pressure is the result of the weight above us. Now there's a couple important things that we have to understand as we go into this. And one is, it's actually Pascal's principle, I believe, that if I have a continuous static fluid, and we'll apply it to moving fluids, but for right now we're doing static, that the pressure at the same elevation is always going to be the same. Because you can go through and argue it pretty simply. If I'm here, I'm going to have equilibrium between air pressure pushing down and air pressure pushing up. Then if I come down, the difference is going to increase by the weight of what's above. And if I go sideways, it's got to be still equal in both directions. Come back up, I will have gone up the amount of weight that I lost. So as long as I have a continuous fluid, the pressure at one elevation is always going to be the same. So in here, the air above my head is only going to the ceiling. But there's continuous air going out the doors and to outside. And so effectively, the weight of all the air above my head here is the same as it would be outside because of the continuity of the fluid. That's actually an important thing to keep in mind. Otherwise, you get really confused about, well, this chamber is shaped differently, and so the pressure should be different. It's not. It just depends on the elevation. So here we have an example of a cylinder with water in it. And so using the principle I've said, let's assume that the top is open to the air. So what is the pressure on the top equal to if it's open to the air? Okay, same as the surrounding. It's atmospheric pressure. Now, if I go down to the bottom, I'm going to have the force acting on the bottom is equal to the force that was pushing down on the top plus the weight of the water. So first thing I'm going to calculate is, what is the force pushing down on the top? And using our relationship between pressure and area, since pressure is force over area, then force is equal to pressure times area. So the force on the top is pressure atmosphere times the area. Now if I come down to the bottom, I have the weight of the water, mg, plus, of course, I still have the force on the top being distributed through the water. So the force on the bottom is equal to the force on the top plus mg. Right? Bigger force because I had the force pushing down on the top and the weight of the object. And that's pushing on the bottom, so the pressure on the bottom is equal to the force on the bottom divided by area. Now, if I put all of my things together, I'll be able to determine how much the pressure changed. But there's one thing I have to do in between. You see that little printed thing that says volume is equal to area times height. That is specific to a cylinder. So this derivation, this little derivation I'm doing is only for a cylinder. But it turns out to be universally true. We're just showing an example that is easy to calculate. So with that relationship, if the volume is area times height, then I can say the mass is equal to density times volume. Notice without a vector sign, the dot means times. Since density is mass over volume, the mass must be density times volume. So the mass is equal to density times area times height. So if I put that into my equation here, the force at the bottom is the force in the top, which was pressure atmosphere times area, plus mass, density, area, height, times G. Notice there's an area in both of those terms. Put that into this. Way around space. And my A's will cancel out. And I'm left with the pressure in the bottom is equal to pressure atmosphere, because that was the pressure at the top, plus rho GH. So the pressure increase just depended on the density of the fluid. Density of water is 1 gram per centimeter cubed, or 1,000 kilograms per meter cubed, multiplied by the acceleration of gravity, multiplied by the depth, which in this case was h. The same is true with air, but the density of air is about 1/800th the density of water, and that's why the pressure difference is very big. Now, something that, how many people here scuba dive? Okay, two people scuba dive. When you're scuba diving, you learn some simple approximations like how far underwater do you go before you go from 1 atmosphere at the top to 2 atmospheres? Okay? The number they remembered was 15 feet. We can now calculate that because we can say if delta P is equal to 1 atmosphere, which is 1.013 times 10 to the 5th pascals, if that's equal to density of water times G times the height, I can quickly calculate the height to get to 1 atmosphere. So ten to the 3rd kilograms per meter cubed, that's the density of water. 9.8 meters per second squared. That would be, of course, the acceleration of gravity. And so if you put that in your calculator, what do you get? $10.3? 10.3 meters. So for rule of thumb, you generally learn that if you descend 10 meters, you'll go up by 1 atmosphere. Descend another 10 meters, you go up by another atmosphere. Now, if you want to do that in feet, a meter is a little bit longer than 3 feet, right? Meter's about 39 inches, 3 feet is 36 inches. So it's more on the order, I think if you convert that to feet, it's somewhere around 33 feet to go up by 1 atmosphere. Got 10 minutes left. Weight versus pressure. This is a, let's say, philosophical question. It's not one we're going to do a calculation on, but it's something important. if you have a dam and you have a small little lake that's 20 feet deep and goes back 20 feet, you put a dam up there, strong enough to hold that. And then what if somebody decides to just excavate a whole bunch of land behind that? So instead of going out 20 feet, it's now going to go out 200 feet. What difference is that going to make for your dam? You're holding back a lot more water now, but it's still the same depth.
So the water's going out more.
Yeah, the difference is simply you have your dam. So this is looking at top view. You built your dam to hold in this amount of water, and then somebody excavates, so instead of that amount of water, you're holding, that amount of water. But they don't do anything to change from here into the dam.
And they added water to that.
Yeah.
Okay.
Well, you got stream feeding, whatever. Yes, that's filled.
It wouldn't change anything, would it?
That's the correct answer. It wouldn't change anything. You're holding back a lot more water. There's a lot more weight you're holding back. But it's the pressure on the dam that's going to tell you what the force is on the dam. And the pressure only has to do with depth. Now, this principle seems bizarre, but a simple experiment that people have done that's really awesome is you take like a strong pipe, a little straw, but a really strong one, not just one made out of plastic. You fill a keg up with water, and of course they did this back in the day when they were all wooden kegs. Fill a keg up with water, and of course it holds because it's strong. And then you have that straw, and you put water 10 feet high in that straw. The weight of the water that's 10 feet high in that straw is really small, far less than a pound. But the pressure it adds is really large because the density of water. And so you burst the keg having about, let's say half, because you increase the pressure so much with the height. So if they had done something to make the water level higher, that would have caused you a problem. But making the water go out away from it more doesn't cause you a problem. That leads us to other things like buoyancy. How much water does it take to float a boat? Does a boat float differently if it's in a small pond or if it's in the ocean? The boat is held up by the pressure of the water. And the water pressure just changes with depth, assuming the water is the same density. It doesn't matter how much water is around the boat, as long as you have enough water to cover the surface of the boat. So if you were to make and this is ridiculous, of course, if you were to make a shell with the outline of a boat, and then you put the boat inside, you could float the boat in a cup of water, as long as you have enough water to completely fill between the shell and the boat. Good to know, right? Because you're totally going to do that someday. Okay. Not going to talk about capillarity here. I do want to give you a problem here to do. What is the maximum height that a tube with a pressure of 0 at the top can pull water up from a lake? That is, you have atmospheric pressure pushing down the top of the lake. You have a tube that starts completely submerged, and then you pull it up and you keep going up until the pressure at the top of the tube is 0. We call that, by the way, a vacuum. Pressure cannot go below zero because pressure is force per unit area, and it's always into the surface. So when pressure gets to zero, there's no force into the surface and just stays at zero. So if I pull that hose up like 500 meters, the water level will stay the same everywhere from your answer to the maximum height. I forgot what your groups are, and I didn't bring in the paper. Let me look up your groups real quick because I want you to work this in your homework groups. If you remember your groups, you can already, get with it while I'm looking it up. That's not it. Genius. I thought the participants was where I saw the groups. Management groups. All right, so here are the groups. We have homework group 1 is Wes, Trace, and Nathan. Homework group 2 is Michael, Emily, and Max. Homework group 3 is Andrew, Sarah, and Kaylin. Homework group 4 is Mira, Ryan, and Lydia. Homework group 5 is Madison, Sarah, and Clayton. And homework group 6, DJ, Leslie, and James. And when you have your answer, raise your hand.
What does maximum mean? What does maximum mean?
Like I said, if you take that hose and you just keep going forever, the water level will only go up to the point where the pressure is zero. It won't go up any higher. So it's the maximum height you can actually raise the water. Yeah, 10. It's this number right there. Yeah, the pressure is off. Pascal. It's that's just my handwriting, but it's the same pressure as you see right here.
Okay. 0. So that's good.
Yes. Okay, so we've got our group with an answer, and I think you have enough room that you can just do it on the side here that's not written on. I'm going to change the color to ink real quick.
Question though.
Yeah.
I keep forgetting the units for the density.
Kilogram per meter cube.
Thank you. Okay. So, right. We have a lake. We have a tube. So we know that there's no pressure in the tube.
At the top.
At the top. So whatever pressure is here is going to travel up. And we know that the pressure there is this value here. We know that there's an equation for pressure, which is pressure equals the height times density, which is not a D, and G.
No, technically that's delta P. It's the change in pressure.
Oh, change in pressure. So if we want to solve for height, which is what it's asking for, the maximum height, which would be the point here, that H is equal to that delta P over the density and gravity, which we have all of the data for. We know that P is this right here, the 1.01 times 10 to the 5th. We know
Minus
the...
zero.
Hmm?
Minus 0.
Oh, minus 0.
And you don't have to write that down because it doesn't add to it.
But it's an important idea. We know the density of water because we were all taught that at birth after walking. That is 1,000 kilograms per meters cubed. And gravity, we were taught after we learned water, which is 9.8 meters per second squared. When you plug all of this in, you'll get an H that is equal to about 10.306, and then as significant as you want to get. I somehow changed slides.
That's okay. And you'll notice that's actually the exact same calculation we just finished doing.
Yeah.
We're going up to 0 instead of down. All right, have a great day.